l'italiano, anche se il colloquio sarà in inglese. Facciamo intanto l'introduzione in italiano, quindi siamo molto contenti, ovviamente onorati di essere qui con noi oggi. E il professor Mézard ha ricevuto, si è laureato in fisica alla Supérieure di Parigi nell'80, PhD sempre in fisica, sempre dalla stessa istituzione, quindi l'École Normale, 4. Dopodiché ha cominciato a girare, è venuto periodi molto estesi a Roma, alla Sapienza, dove ha collaborato con il professor Parisi a scrivere i lavori sugli spin glasses, un famosissimo libro, e tutti gli altri lavori, dopodiché si è spostato a Santa Barbara di Berkeley. E è uno dei teorici sulla meccanica statistica dei sistemi disordinati, sistemi complessi, a partire effettivamente anche sulla teoria dell'informazione, scienza dei computers. Grazie a tutti questi contributi ha ricevuto moltissimi premi, cito solo la medaglia d'argento nel 90, il premio Ampère della Science francesi nel 96 e molto il premio Onsager dell'American Physical Society a marzo quest'anno durante il March Meeting. E oggi, e oltretutto questo Giorgio Parisi e Riccardo Zecchino. Questo spiega anche perché conosci molto bene l'italiano. In particolare il talk, come vedete dal titolo, parlerà sulla teoria dell'informazione e in particolare la teoria dell'informazione. Siamo molto onorati e molto curiosi di sentire questo.
Grazie mille per l'introduzione. Mi dispiace in italiano, ma sarebbe stato un po' pesante per voi perché le parole scientifiche non così facilmente. Ma sono completamente felice di discutere, di avere in italiano e anche se volete interrompermi non mi fa nessun problema, al contrario. Talk today about Boole Shannon of data science. It turns out that was the 200th anniversary of George Boole and 2016 anniversary of the birth of Claude Shannon. Interesting topic to share with you today. It was a Boole Shannon lecture. And actually, the talk that I gave introduced a third actor, which is Ludwig Boltzmann and statistics and phase transition. It might seem a bit odd in some sense to invite for the Boole Shannon lecture, to invite someone who is an outsider, both in computer science information theory, the two fields of these two giants, invite a physicist. And in fact, there are many physics concepts which are very essential in contemporary computer science and information theory. Of course, on the side of information theory, the very itself is between. So I will insist a lot in particular on the essential role of phase transitions in a problem at the core of computer science theory. So I will start with the statistical physics itself. Start with this famous sentence written by Phil Anderson in an article he had many years ago now. More is different. In some sense, if we go a bit more than a century ago, we could have thought, a bright physicist had thought that that physics was understood, and so it was well understood because we had Newton's various forces, but sense, and that is what was discussed in this paper by. One might think that once you have these laws, basic forces in nature, physics is over. We all know that it's not the case, and just to give a picture that simplifies why it is not the case, the water around 170. And we know that it can be either in the form or in the form of ice, glass, or crystal. It may have many different. And so this very question of phase transition has been and it is at the core of the. So I will start basic concepts in phase transition. Drifting to decades before in 1944, the dispute or the kind of that was around was how atoms, molecules, interactions that don't change can have different assembly themselves in a very different. And it has been shown by the solution of Onsager of the Ising that it is a statistical effect, that it's related to the exploring Boltzmann weight. And Boltzmann weight in itself, it was done with the Ising model of a magnet, where you have magnetic moments which can point up or down. It is lower when the two spins are parallel. This configuration is more probable. All this is the ordered state is so easy to understand in some sense when we teach it. That's in general a couple of hours to explain what it is. It is an ordered state which is not frozen, in majority pointing up, let's say, but the ones which are pointing down fluctuate in time. And so it is a collective state. Being a collective state, it is very robust to perturbation. It takes place at a very well-defined temperature. For iron, this is the temperature. It is related to a spontaneous breaking of a basic symmetry of the problem, which is a symmetry by flipping all the spins. This is the well-known curve of the resulting magnetization versus temperature. Above a certain critical temperature, it's 0, and below it can be either plus m or minus m because of this symmetry that I was mentioning. This is well known. It goes back to 1944 and following years. What I want to study next is the case in which you have the same kind of phenomenon, but in a disordered system. And for instance, in spin glasses, if you take copper and you have some impurities of manganese inside copper, of the order of the percent, 1% or something like that, it turns out that the manganese has some magnetic moment, not the copper. And there is an indirect interaction between the magnetic moment of the manganese atoms, which is mediated by the conduction electron, but never mind in some sense. But what is very important is that this interaction depends on the distance between the atoms and between the spins. So depending on the distance, the interaction will favor parallel state or anti-parallel state. Now, if you have disordered system with disordered positions, depending on the pair of spins that you look at, they want to point parallel or anti-parallel and so on. So it's a mess. It's a disordered system, strongly disordered system. So immediately this has, this in the 70s already has started to be studied, and it took a long time to understand it. In these spin glasses, each spin now sees a different local field. And immediately this points to you on difficulty for the theorists to study this system. If you have the ferromagnet, first rough approximation, you do a mean field theory in which each spin sees the environment created by the fields around it, and you write a self-consistent equation because the spins which are around have the same environment as the spin that you look at itself. So this immediately creates the famous Weiss self-consistent equation. Now, in this case here, technically, if you write mean field equations, you write coupled equations for the local magnetization of each spin. So you have n spin, you have 10 to the 23 spins, 10 to the 23 equations, and you want to solve that. So you understand that this has created a little bit of time to think about how to handle that. And basically, I will not give you any course on spin glass. It takes a long time to explain the theory of spin glasses. But basically, in some sense, what has been done is to imagine writing these 10 to the 23 equations and doing a statistical analysis of this equation, basically. And so instead of writing a self-consistent equation for a local magnetization, you write a self-consistent equation for the probability of the local magnetization. Now, this would be simple if it would be like that. This was the first attempt, but then it turns out that there is complication. The main complication comes from the existence of what is called frustration. When I told you that it was a mess, it is a mess because imagine that you have three spins which are at distances such that all the interactions are anti-ferromagnetic, prefer the anti-alignment of the spins. Then if this one points up and this one points down, what will be the preferred state of this one? Depending on the interaction that is most relevant, it could be one or the other. But then you see that you have a degeneracy in this problem, and you have you cannot satisfy. Basically, one complication is that you cannot satisfy all the local constraints, contrary to the case of ferromagnetism. And in fact, if you look at it from the point of view of optimization now, if you write down the energy, the total energy, which is the sum of the pair energy of the spins with ferromagnetic or anti-ferromagnetic interaction, and you ask, what is the ground state? Just this simple question. This turns out to be what is called the NP-complete problem. That is, it's a problem for which there is no known algorithm that is able to solve the problem in polynomial time. All the known algorithms take exponential time. Like the simple enumeration of the 2 to the n configuration of the n spins, let's say, is obviously exponential. So because of the frustration, the spins freeze in random direction. It's very difficult to find the minimum of the energy. And what happens is that there is a lot of degeneracy. And so you can have, if you have found a low-lying configuration with low energy, it may happen, and in general it happens, that there exists somewhere else another configuration of the spins, which also has a low energy, but which has nothing to do with the previous one. It's not obtained by symmetry, it's very different. And so this has some very strong impacts on the dynamics, it creates aging effect. I don't want, again, to give a course on spin glasses, but let me just mention one point which I like a lot. Spin glasses are totally useless. Nobody has found a way to make a device out of spin glasses. But already when I started myself on spin glasses, which was okay, I don't know if I should say it, but probably 83, already thousands of papers, and now there are tens of thousands of papers. That's because it is pure intellectual interest. That's what is very funny, and you will see some is that the spin glass theory or the corpus has been developed. I borrow another again from another paper by Phil Anderson. He had a Physics Today paper on spin glasses, spin glass cornucopia. And cornucopia is this object that I have. He knows what is a cornucopia, so I put a picture of it. The cornucopia comes from the fact that it has been applied in many different situations. And to give you a hint at is why. In some sense, if you look at it from that at the beginning of statistical physics and condensed matter theory, you were studying, or our ancestors were studying systems. All spins are alike, ferromagnet, and so on. In some sense, it's easy, as I was saying, you can have at least one representative spin, one representative agent. Gradually, you but spin, you could substitute the name spin by bit of information, as I will tell now, agent on a market, neuron, environment. So even the nature phase obtained in such system is very difficult to of this n-coupled equation that I was before. So it's no longer a theory of a representative in the market, for instance, but if you have a market with many agents, you need to do the statistics of representative agents, as we did in spin glasses. And the purpose of ideas and techniques, so cavity method and so on, for spin glasses, they can then be applied to heterogeneous systems. And that was why supported and has served as a cornucopia. We know when you have agents on the market, it can result in very strong effect that you can see, for instance, of the Dow Jones. So this was absolutely crucial in computer science, and they have chosen 3. So the first one is about error correcting. It is related to Shannon. We use error correcting codes every day. We use a device when we communicate with a satellite, communicate with our cell phone, there is an error correcting code. When I enter something in the computer or I take it back, there is an error correcting code. Actually, error correcting, we use it much more than that. When I talk to you, we both use an error correcting code. But the language is redundant, strongly redundant. That is, if I have mispronounced a word, if I mispronounced, well, you understand. Because the closest to mispronounce is mispronounced automatically. So we have a lot of correcting codes in the act of lecturing. Actually, that's something extremely important as a teacher. All the teachers in the audience, they know that the student, so to correct the error by adding to what you are saying, to the lesson all the time. There is a lot of error correction in biology. I will not have to elaborate on that, but in the from a retina to the brain, in the transmission of genetic information. Now, Shannon, the great man, worked on that in his beautiful 48. He has thought about formation, entropy, how to transmit correction, and how to compactify it. And these are absolutely crucial concepts in the same corpus of knowledge. So this is basically the scheme that is used in correction. Imagine that I have an initial message. Then I will code it. I will encode it. Then the coded message will have n bits with L. That is the redundancy that I was talking about. The coded message through a channel. That's my message to you. The channel is noisy. Now you have, and the decoded message hopefully is the same. That is the idea of error. Now how it works just by added redundancy. Okay, so here is an example. Code. Imagine that I want to transmit an image like that. Repetition code, so these are, I don't know what's the size, but by 100. It's 10,000 pixel image initially. Now, one thing that I can do a very minded code, which is repetition code. Instead of I send 3 times the image. Okay. When I send 3 times the image, I get 3, and here I have a certain noise level. I get 3 initial image. Now, for each pixel, rule, I take the top left corner here. Do in this decode. It is not equal to the previous one. Much reduced, much less noise if I had not done this repetition. So repetition, just to give you an idea of what coding and decoding is about. Very simple-minded code. The discovery of Shannon is that if you look at languages, there exist codes which are such that they will be able to transmit the information without. That is not obvious. If you think of repetition code, you can do the computation. It's a very trivial computation. If if the channel here flips a bit with, say, 1%, of what is the number of errors in the. Now you can say instead of sending 3, I send 5. Of course, the more you see, which are smarter than repetition, which are without any error. And Shannon, in her paper, invented a code, which is the perfect code in some sense, and I will elaborate on in what sense it is. Actually, it's a code ensemble. It's a family of codes. It's called the random code ensemble. So imagine that messages of length n with a binary alphabet of. Now, what he says, well, I will in such a way that the only messages that can be sent in what I call the code book. I have a kind of all the messages which I am allowed to send on called the code book. And so what I will have a coder, which is the first mapping between the message, a word in the code book, that I know that code book. So imagine it becomes complicated. So imagine that so this is a binary letter, so it's a cube, and this is my code book that I'm allowed to send. Now, in Shannon's ensemble, you can imagine very well what will happen. That is, if of these words here in the code book, but it means that it will have some bit which is flipped to there, for instance. It will go from here to there, and then by mapping back, finding the closest code word, the word in the book which is closest to the message. So you could imagine that, okay, let us choose these as a on the hypercube. Now what Shannon says is be more elementary, say, in some sense, and we just build a random code ensemble with a code book. We take our hypercube. Now, everything has to do with the thermodynamic limit, actually. The thermodynamic limit, large size limit, so you send big images, let's say, in the before. And you have, the code book is also large. You have a rate, which is n. So the smallest the rate, the more redundant is the code in the length before. Now, it means that you select on this cube, which has 2 to the n vertices, you select of them. Now, in the thermodynamic limit, of course, the fraction vertices which are occupied is very small. It's 2 to the L over 2 to the N more than 1, of course. It goes to 0 exponentially. It's a very, this is not something that is shown on the picture, but so you have to imagine with very sparse code. Now, what happens, imagine that I have sent this code. Maybe it is corrupted by noise, and it is here. Simple code, code that you can study analytically in all details. People who have studied the statistical mechanics of disordered systems, it's rather closely related, and the way to analyze it is very closely related to Derrida random energy model. It's very much the same. When you study the performance, all geometrical. It's the geometry of this cube in large dynamics. Pick up random points. Now, once you take one of these random code words, you corrupt it, and where is the closest code word? Is it the same as before? You look at you look at the probability that it is. So it's the probability of a perfect transmission. And you find that in the thermodynamics, probability has a sharp phase transition threshold. That is, below a certain noise threshold, you transmit exactly this it, and it's a decreasing function of the frequency you have, of course, the more All this can be computed. It's called Shannon's probability. And he has also shown that there is no error correcting code that does better than that. He has invented and shown that there is nothing better. So it's sometimes called the Shannon. Okay. Shannon bound is a phase, a geometrical phase transition, very similar to the glass transition of the random. Now, there is one small detail in code, which is that it is totally because there is a step which is a step code. I told you how you decode. You take what you have and you look at the code book. What is the closest code word? Okay. Here there is a small problem because the code book has size 2 to the L, and L is N. So it's a very large code book. So with something with N equal 1,000, let's say, it cannot do it. 48, the community of scientists who are correcting code tried to invent and have invented, which are of the same nature as I was saying before, but in which you can. So the reason why you cannot decode in it has no structure. You have taken random points on the cube. Which of the random points is the closest? There is no other way. If instead you choose a random point on the cube with a certain structure, a geometric structure, algebraic structure, there is a Galois field behind, and so on, beautiful mathematics behind. The more structure you have, the more hints you have of how to decode. So in general, what has happened is that you are build a structured code. That's like, for instance, density parity check codes. These are based on that you take a certain bunch of spins and you say all these spins has to be -1. That's a constraint. Constraints like that. And now, if you look, basically you have the curve of the code that you had again infinite time available. That is, if you to spend exponentially large time on decode, use less. And then you have a practical algorithm in the cell phone, let's say. All of them have phase transition, sharp phase transition. So the ability of your to tolerate noise is a phase transition. And so the whole has been to try to move this curve here with the algorithm, to move it as close as possible to the Shannon. In the recent years, there has been enormous on that, and now we have what is called code on many types of possible channels. Let me explain maybe a geometric how is the phase transition that I was mentioning. Imagine that this is my code book. These are the code words I have chosen. I have sent this one. It through the channel. Because of the noise, it is corrupt. Different. This distance, the distance between this and that is the characteristic of my channel. So I know that at this distance received, there should be a code word. The sphere which is here is still exponentially large. Search it like that, I have to be a. So now what may happen, there can be either there is a single code word and there is no landscape and I will find it easily by algorithms, or it has a lot of metastable states, the algorithm. And so basically what happens is that you have the simple phase in which the code is in a smooth landscape and you find it easily. You have the complicated phase here in which the algorithm does the solution because there are a lot of metastable states on top. And there is the one in which it's completely impossible. The code words everywhere. And so you are lost. Maybe now let aside for codes. I hope I have convinced you that on error correcting code, a very crucial theory, what it is about. To address a second problem, now to, in some sense, to Boole, called the satisfiability of Boolean formulas. And again, it's a problem which is a field. The field is computational complexity. So now, if you look at discrete optimization problems, let's say, there is a whole theory of computational complexity which classifies the problem. Imagine that you have a problem with n variables, and you want to find, you have an energy function of this n variable, you want to find the minimum value of this function. Optimization problem. Now, if you want to do, you can ask if it is possible to do it with some algorithm, and what is the time required by the algorithm. And now there is a whole theory of complexity developed by Cook in the which says that in these problems there is a category of problems very hard, and they are very hard in the sense that to run exponentially in time. Some of these problems are well known. You have heard about them, like the traveling, going around many cities and going back home. This is a typical NP-complete problem. Whether these problems are really exponential, whether it really takes exponential time, is an open problem in this field. If one of you comes with a polynomial or the traveling salesman, for instance, then all problems in this category, all these energy functions also in polynomial. So it's the NP-complete problems are the hardest one, and based on the analysis by Cook of one of the case satisfiability, and I want to explain. It's a very simple problem. It's the first problem that was shown to be NP-complete, understood first. The problem is n binary variable, xi, which are in 0 means false, 1 means true. Local variables in the sense of Boole, negation. The clause x1 or not x2. You have done a little bit of logic. You know that this is satisfied except in one case. There are the 3, that is 8 configuration of the variable x1. And there is one of them which violates the clause. 1 is false, x2 is 3, x3 is false. In that case, the constraint is violated. 7 cases, the constraint is okay. So this is very simple. It's when the clauses have k variable, here k equals 3, it's called k satisfiability. Now, people have studied this problem of k satisfiability, so it's hard. In the worst case, the analysis of Cook is the worst case analysis. Now, people have studied that case in a random ensemble again. Generate a k satisfiability formula. Just choose the clauses at random. You have n, you choose m clause, each clause picks up 3 variables, negates it with probability 1. Action problem can be mapped to satisfy the standard form in logic, conjunction. Now, if you look at the limit in which you have a large number of variables, constraints with a fixed ratio of variables of called alpha, what you find is the following. Numerically, what is the probability that a randomly generated formula, that is, it is satisfiable? And you do, there are some algorithms which are able to do too large. They go through analysis of decisions, let's say. They are exponential algorithms in general, random, and this is the curve that you get with n equals. So the abscissa is the number of constraints, and the ordinate is the probability that a randomly is satisfiable. So, of course, this probability is more constraints you have, the less likely it is that it's satisfiable. When n equals 50, you get a n equal 100 is a green curve, it becomes sharper. It becomes sharper and sharper. It can be shown that this goes in the large n, although it has yet that the location of this is stable in the large n limit. It might oscillate. That it goes to a step function. But the step function, the fact that the step function has not yet been proven, except in the large K regime using so this transition again in 3SAT. One thing which is not more than amusing is that if you look at the computer time it has taken to generate this curve here, this is equal 50, and that's the log of the computer time, that's the branches that have been explored. So this is a number of constraints. This is for n equal 50, n equal 100, n equal 200. So you see log increases fast. So these are very hard problems. But so these are exponentially hard. The time grows exponentially with the size of the in this intermediate phase close. This has been extremely important from the point of view of exchange. I have spent a lot of time in my life with colleagues from other fields. And one thing which is is that you happen to have the same interest with the discipline. That is, you find the same problem crucial. Same problem is crucial. That is a phase transition for the physicist. We know that there is space there. And it happened that here also the computer science is extremely interested in that phase transition because it is the way to generate the hardest possible. So now using borrowed from spin glass theory that I spare you, let's say the same as spin glass, and then the statistical analysis of the. We have obtained a certain number of results using that. Located the precise value of the phase transition obtained by solving a nonlinear integral equation than a slide, and it's not interesting in that. But the thing which is much more interesting than that is the landscape. So this is again the density of constraints. If I really not 2 but 3 phases, that you take again a configuration of these are binary variables, so it's again my that I was mentioning before, and I color in green the points of the hypercube that satisfy all the constraints. I have an easy phase below a certain first D, dynamical, and in this, so that the vertices which are colored in green, it means that if I have a solution that I can move to another one by flipping one. Big disaster on this landscape, which is split into potentially many disconnected clusters, small clusters here. Which appear. It means that if I am here, some solution by moving the hypercube, but then I will be confined and somewhere else, very far away, the cluster of solution. And it is extremely difficult because it involves a collective selected direction of a large number of spins, total numbers. And then comes the SATA and SAT transition, the one that this famous 4.267 threshold, green point. So to give you a pictorial taking place in this system, we have 3 phases, number of violated constraints, as along. This is going in a random way. We have a case in which there are lakes of solutions and many metastable. And here I have no. So the immediate phase is actually typical of phase. It's a phase in which we have states, actually zero energy state, which are very well very far from each other. So actually, one thing that had not been understood until we came in this domain is that the difficulty close to the SATA-SAT solution transition of this glass phase, such that it's like in all the physics of glass. If you look at the relaxation time in a glass, it becomes the glass ages, and it is the same thing for the algorithm. That is what, if you take the algorithm that work well in this phase, and they start to have a relaxation here. It is to the standard algorithm. So based on the analysis, we invented another called survey propagation, which is actually able to solve the problem in the glass phase. But this needed, in order to invent it, this needed to understand all these geometry of the glass transition. Let me use this example of the importance of phase transitions on satisfiability formula. I just want to give you a third example of phase transition. Again, in theory, it's some recent work that has been done. Compressed sensing is fashionable in the last 10 years, a bit less than 10 years. It's a kind of new frontier of information theory in some sense. You all know that because you compress it, similar to the picture that you had originally. For instance, by taking the wavelet coefficients, you take the composition of the image. If this one has 65,000 coefficients, you keep only 25,000, the most relevant, to get this image here. This is used in all these compression algorithm that you use every day. This is very well known. This is data compression. You could say, first of all, I would like interesting signals can be compressed. Actually. Interesting signals are sparse in some basis. Because if you take, for instance, you take a picture which you cannot just random black and white. Very interesting. You can do some statistical analysis. So this data, this is very exploited. The data immediately in compressed way. Is it to go through the detour in which I take the full, then I compress it. If you are able to do that, well, for pictures it's not very relevant, but if you start about magnetic resonance, then it means that maybe instead of staying in the machine, you stay only 10 minutes. And that is extremely important, and that explains why people have been working on that. So it has a lot of applications. I will not go through all of them. I just want to give you a simple example on working in recent years. It's called, and I will illustrate it on the case tomography of binary mixture, which is a binary mixture, a white material, and you would like to understand what is the composition. The usual way to do that is you go to your favorite, I don't know which one is nearest to you here, but maybe in Trieste or something. You go, you shine synchrotron light, you detect here. Basically, imagine that the absorption rate of the black and white are not the same, which is a generic case. Then basically the intensity that arrives here in each pixel of the camera that you get the fraction of black and white along the line, along each ray. I have a number, I know that there is, I don't know, 1% of black, here I have 5%, and so on and so forth. I have all these numbers. Of course, with all these numbers, I cannot reconstruct the picture. That's all. Now, imagine that I have here L pixels. It turns out that if I rotate, and I rotate, okay, this is called what you are doing here is called the Radon transform, and you do the inverse Radon transform. It's like doing Fourier transform and inverse Fourier transform. You do enough measurement, as many measurements as you have pixels, there is a way to come back to the sample. That's what people do. That's what is done regularly, every day. Now, imagine the situation, which is very frequent, in which I look at a sample in which the size of the domains, these famous white domains that I have here, is a certain correlation size. Typical size is psi. My pixel size is 1. Imagine that I am in the range where psi is much larger than 1. So it means that the information content of this image is not L square pixel, not L square bits. It's much less than that. Actually, I could have a description of the image which is much shorter than giving you the value of each bit. I could tell you where there is a bubble on the top left which has, okay, it would be complicated, but I could still make it much shorter. So it means that this image can be compressed. This image has much less information than L square. Now, is it possible to acquire this image by doing less than L square measurement, which is a standard? Now, this picture digitalized on a 1,000 by 1,000 grid, that is with 1 million pixels, could be reconstructed with only 16 angles. 16 angles, each of them does in parallel 1,000 measurements. So it's a speed up of a factor 60. Speed up of a factor 60 is very important when you start to think in terms of application and so on. So how can we do that? Well, one way that we have been using, and it will be mainly the only equation that I will use, is to use a prior knowledge. Basically, how you can imagine, what you are doing here is that you are reconstructing a signal by doing less measurement than unknown. How can you do that? You have to add extra knowledge. The knowledge that I add is a prior knowledge. I know that I am looking at domains. I have a system in which I have, it's not a totally unknown problem. I know that it is an alloy with domains of A into B and so on. And so having domain is something that I can encode. See, if Si is a pixel, I can say that neighboring pixels have higher probability of being equal than being different. A standard easing type prior, which will help, and then you can adapt the J in order to have the right correlation length. So using that, you have this prior, and then you have for each measurement, so a measurement will tell you, for instance, in this direction, I have looked at all these pixels, and I know what is the sum of the spins. I know what is the fraction of the black and the white, and the white, because this has been measured by the synchrotron. So I look at this measure. This measure incorporates the prior knowledge, which is here, and the measurements, which are there. And using the prior knowledge and the measurement, I try to find the value of the pixels which has the largest possible probability, minimizes energy, if you want to say. How I do that is not trivial. I mean, it requires, again, this is again a disordered system because the measurements have random numbers in them. And so again, I will use my self-consistent coupled equations with n variables. But now I will not do a statistical analysis. I will implement them on the computer. I have 1 million coupled equations they put on the computer. You can do it. And that's how you run the algorithm. Now, one thing that I want to emphasize is that in all these problems, if you look at the number of variables and the number of measurements, you have, when the number of so this is number of variables divided by number of measurements. You have an easy case in which the number of measurements is larger than the number of variables. That's trivial. You use a standard algorithm. Then there is a threshold in which it is not trivial but doable. So it's still doable in the sense that our self-consistent equations converge. We have a convergent algorithm. Then there is a hard phase, and then there is an impossible phase. How is it related to the energy landscape of my system of pixels? In the easy case, I can have one ground state, which corresponds to the image that I am looking for, and I can solve it by an algorithm which is called belief propagation, which is basically the iteration of the mean field equations I was mentioning at the beginning. Here, I have a hard problem in the sense that there is a single solution. It is hidden somewhere, but there are a lot of metastable states. And in an analogy with physics, this I call the crystalline state. This is the one that I'm looking at. And these metastable states, they are glassy states. So here I am typically in a situation in which my belief propagation will not converge because it will be trapped there. And what we have invented in this case is an algorithm that nucleates the crystal. It will focus, it will put more information on some subset of variables so that once this subset of variable has been found, because I have done more measurement on this variable, it will nucleate the crystalline state in this region. And once you have nucleated the crystal grows, like crystals like to do, and it invades the whole system, and it goes to the solution. And here is the impossible phase. So let me give you two examples of not practical. These are still academic images, but this is called a shape-Logan function in it, and this is the number of variables divided by measurements. So L1 usual algorithm stops ratio is equal to 0.5. It degrades and it does not find the solution. The standard of the mean field equation is able to go to a number of measurements smaller, twice smaller actually. And if you look at the one is the crystal, it goes all the way to the optimal possible. It means that all these ideas, they can be turned into algorithms. If you know that what has stopped your algorithm is a glass phase, looking for a crystalline phase, you invent a new algorithm which nucleates the crystal. And so this is the same picture with a picture of Lena and for the one that nucleates the crystal. In a nutshell, in compressed sensing, linear problem, because the measurements here are linear measurements. Signal, we have a number of measurements. We have a kind of, these are the measurements that you know. This is a measurement matrix, the signal. You want to reconstruct the signal. But you are in the number of measurements is less than the number of, invert the linear problem. You don't have enough information. But you an idea, which is the fact that the signal is sparse. That is, in another, the signal has a lot of zeros, and so you, in the way you analyze the system, of the original system of the original signal, say, I want to invert this linear problem in a fast way. So, I have a kind of. I thought that coming here, I step beyond, and I will go to something a bit. In the last 3 I have, and I wanted to take you to and the impact of all these ideas on some evolution. So coming here and discussing of the scientific picture that you know very well, and at a Boole, and you see it from a and you solve the equation. There should be a d and square root of z. Okay? Now, that you have found, you do the experiment. This is d, this is square root of z. And what I should say that this is fake data. It's not my experiment, I have not done it. But of course, Galileo itself, I'm not sure how it was fake or not, or adapted. This whole story. But my data completely fake. It's just for the purpose of showing you. So but this is to tell you what is a scientific method. The method is to say, I have a model. I have an idea of the world, of how the bodies behave. My idea tells me that there should be a linear relation between d and square root of z. I plot, and then I compute the best alpha that minimizes the mean square error. Well, we do that every day. Maybe someone a bit tells me, well, there is an effect that you have not taken into account. There should be an effect in proportional to square root of z, but z. They do another fit with 2 parameters, beta, and maybe it is a bit better. Someone comes with a 5-parameter fit and tells me, look, do that, you have a curve which fits much better. of course, I have 5 parameters I should be able to do. It's attributed to von Neumann that I should be an elephant, and wiggle is trunk if I'm enough with my data point. So this is how we go usually. You find a small number of parameters, we fit, and we see if it works. Imagine that you have now another possibility which is open in the phenomenon. I have 1 million variables, but 1,000 parameters. Should I do a 1,000 parameter? This we know Neumann has told us that the 1,000 elephants is not a good idea. But the thing that you can do is to say, I put 1,000 possible phenomena and regression parameters, but then I add a prior. Prior is to say, look, I want to have the fewer possible of this parameter, of these that are non-zero. I will put a penalty. There is a fitting parameter which is non-zero. I pay something. So I will try to fit my data. I have not chosen which are the relevant fitting parameters. But I put a penalty. And then the system, I have enough data, the system will tell me, oh, it is this and relevant. And I get a very good fit with 3 parameters, 7 parameters. And then maybe what I should do is parameters, the causes of my phenomena. I'm trying to understand if there is a causal relation and so on. That hint what is the model. In some you have these very big coming from the analysis of expression of RNA chip experiment. It's very noisy, but you have, and from that you want to reconstruct a kind of network of production of gene, how a gene regulates another one, and so on. You don't well. You have in some cases you have some hints, but in most you don't know which is a gene that really will capture the expression of another gene. What are the interactions and so on. You want to reconstruct it. That's exactly. Of course, this is probably how we will be cured of this going much in this direction of the statistical, which produces some new type of medicine. Of course, it doesn't give you the model, it doesn't give you the understanding. There are other steps that have to be understood. That once you have understood, probably relevant, and this other one, and so on, you still have to. But I think that it goes one more.
Inspiring colloquium.
Sì, d'accordo.
Che uno mette nella punti non nulli, lì c'è un'arbitrarietà, produci.
Ah, sì, sì, diciamo,
quell'arbitrarietà lì è quanti ne
immagina per esempio che voglio fare il fit di radice di z metto, che ne so, 10 di queste potenze. E poi metto, allora, il problema è di fare, means minimizing, I go back, sorry, parameter times the number coefficient. Or maybe you can do, which says that as soon as you have one of the fitting alpha, let's call, you put a penalty in proportional to absolute. That is something that will favor the case in which alpha.
But depending on this function that penalizes,
here there is freedom. Yes, here you have to.
In what way is this compression of parameters from what Fisher prescribed with what is called now Fisher test, which is basically a comparison of the difference in chi-squared or whatever measure you want to use compared to the number of parameters of a fit.
No, well, there has been, I mean, the idea which is new, which is that new, but it is something that has been, that is called last, which is this linear, piecewise linear function. Bring the parameters to 0, and then you minimize. So you basically answering Amos' question. You have one free parameter to choose. So for each of the fitting parameters in your regression, you put absolute value of penalty with a certain coefficient in front. So you have the that you have to monitor. And then you look at the ground state of the minimal value of all this, the sum of the mean square error penalty function with just one coefficient. And this will automatically bring some of the coefficients.
There will only be value of that parameter which preserves the coverage properties of your intervals parameters.
Then
right?
obviously what you have to do is vary the parameter that I have to localize the parameter fit or not. It will be also your choice. But you educate this choice by varying and see if you have some of the answer when you vary the.
Questions?
Probably means my question is a bit up to now. Means you know there is this quantum computing, quantum information. You never mentioned Shannon, Boolean. Means there is any you can say regarding to the age. Means about the quantum era. So how you can it's work with the what you say up to now.
There are many aspects that could be. Maybe I would like to mention one of the most actual one, the one which is closest to the present result. Look at compressed sensing. So the idea of compressed sensing is some prior knowledge. Let's say you will extract more information than what you do measurement. The whole discussion about using such idea measuring wave function. You want to have a relatively small number of subsystem with n spins, let's say, and you want what is so in principle the decomposition the system should have 2 to the n coefficients. Because of the way that the system has been fabricated, you can guess that it's not at all like that. Will involve only a small number of coefficients. So if you're doing a relatively small number of measurements, you should be able to infer experimentally what is the quantum state of your system, having to do all the measurements that you priori for an arbitrary system. It's called, it's a quantum version of compressed sensing. I think it's something.
Ringraziamo ancora il professor Mézard.